Hello and good morning or good afternoon, depending on where you are in the world. From my side, I'm Jakob Kristoferitsch. I'm a senior expert on AUTOSAR methodology. So I'm actually interested in how do you make AUTOSAR work? How does it work in a real life project? How do you work in a vehicle environment where multiple parties, multiple companies, a lot of engineers work together on one big project? So this is my main topic. I have 10 years of experience in automotive software, and I'm one of the co-inventors of CPFlex. So there have been several. It's been an initiative across several companies, but I've been there from the start. Awesome. Over to you.
Hello, welcome everyone. I am Hosam-Eldin Mostafa. I have 7 years experience in the automotive software field. I am mainly specialized in providing an AUTOSAR-based solution architecture solutions based on AUTOSAR. Thank you.
So let's have an overview over what our topics are for today. So we'll give a short introduction about ETAS and especially the different products they offer and where CPFlex fits into all of this. We will talk a bit about the integration challenge. So what happens if you have these big automotive projects? Where are the challenges and how CPFlex can help with that? We will show a demo of our solution and then we will finish with a question and answer session. So yeah, as our moderator already said, if you have any questions, just type them in and we'll we'll answer them at the end. So yeah, what do we offer? We have solutions that cover the embedded DevOps cycle in cybersecurity, the vehicle operating system, software development solutions, vehicle cloud services, data acquisition and processing, and integrated customer solutions. And today we'll be in this corner down here on the vehicle operating systems, which is where CPFlex is located. So the vehicle operating systems consist of two big AUTOSAR-based solutions, the classic platform one and the adaptive platform one. And CPFlex, as the name CPFlex stands for Classic Platform Flexibility. So this already tells you that we'll be in the classic platform today. So how are big projects in the classic platform developed? You have a goal for the whole vehicle, and you usually also have a system design for the complete vehicle. And this system design is developed in steps, in increments, where you have a system version 1.0, a system version 1.1, a system version 1.2. And for each of these system versions, there are then requirements for the individual components. And they also iterate in these version steps. So, for example, for a brake control unit, you have a brake version 1.0, which then again has their own software components or parts in there, which have again versions and are developed step by step. So let's say we are developing the brake ECU version 1.1. And when I made these slides, it was still autumn. Currently, it's winter in my location, but we will consider a scenario for the autumn. So you have leaves on the road, and you want to improve the drive-off behavior. So you want to improve this. Basically, you're standing and you're starting to drive, and the road is slippery, the leaves are slippery, and you want to improve that behavior. So you first need to know, are there leaves on the road? And if there are leaves on the road, are these actually slippery or not? So you get via the bus from the video system a signal leaves on the road. Inside your own ECU, there is a signal layer where you take in these bus signals and then do all of these timeout and initial value calculations and so on, and to then get a signal for your own software component. And to figure out if the leaves are slippery or not, we add a new runnable, that is the RE leaf detector, which does something to detect if the road is slippery. In our case, we say, well, it's going to try to apply the brakes while we are still driving, just in a very small amount to detect if the leaves are slippery or not. And if we are in such a scenario, then we limit the maximum torque. So this requires an update of the signal layer, which is a bigger software component that sits on top of the COM and takes in the signals and does stuff with them. And then we need to update our own component, the slip control component, and then the signal, we have a new output signal that again goes back to the signal layer. So here already in this really simple example, which of course is made up for the purpose of this demo, but very similar things happen in the practice, in the real world. Already in this very simple example, we have kind of a cyclic dependency where the signal layer 1.1 depends on the slip control 1.1 and vice versa. The slip control depends on the signal layer. This is not such a difficult scenario because in current projects, what you do is you create this new system architecture and your new system description and your new ECU extract, and you just do an RTE contract phase where you already have the interfaces, you can already connect them and so on. It's just not implemented yet. And then everyone has to deliver their binary for this new version at a similar time. So what this means is that for every system release, you have a time where everyone has to deliver their software component. And this is kind of a synchronization point. Everyone has to be ready at that time. And that's quite inflexible and causes integration issues. And in many real-world examples, it actually, in our example, you can generate the RTE beforehand because you have the new interfaces and it's just some new added interfaces and it doesn't hurt when they are not implemented. But in real-world projects, this is actually quite a headache because you have the cases where you update versions of interfaces and they are incompatible, so you cannot build an RTE until all the components that use this interface are updated to the new version. And in big projects, this means that you are sometimes weeks without a working software. So this is really a real project in the practice already in existing projects. And if we now move to the world of integration platforms, where many software components are integrated in a bigger centralized ECU, so you have functions that were distributed across multiple ECUs, and they are now moved to these central ECUs, and you have suddenly have ECUs where there's not only brake software, but there is brake software and maybe infotainment software and maybe video or ADAS software, depending on how the system is cut. But you get bigger ECUs with a lot of software and especially many software components from different development entities, partners, tier 1, 2, 3s, OEM, and different functional domains. So all of these problems basically get worse. So you still have your system that develops in increments, but instead of a small little brake ECU, you suddenly have this big integration platform ECU, and inside this system you have, in this example, brake wiper and display. And so you have more parties, you have more interfaces. This whole integration platform becomes integration issue challenge becomes just bigger and more difficult. And integration really becomes a bottleneck in development. So you are stalled, you have to wait until everyone is ready before you can have a new version that then everyone can use to test and so on. And out of this, there was a strong market need for flexibility. So we had requests from several OEMs where they said, hey, we need a solution to this. And that's how we end up with CPFlex. So before CPFlex, you have a monolithic software. This is basically one binary that you then flash on an ECU. You have a monolithic build. So you take all the software, you take the complete basic software, you create a binary or a hex and an HL file, and you use then use that for flashing, for producing ECUs. That's what the factory stands for measurement and calibration. And since that the main bottleneck was the RTE, where all the signals come together and where this whole virtual functional bus is implemented and where you exchange data between all your software parts, the idea was to split the RTE. And instead of a big monolithic software, you have application software clusters where you have parts of the application software, where you have a piece of the RTE plus a piece of CPFlex that is then needed to make it work. And the other thing you have is a host software cluster where you have the complete basic software, you have the runtime environment, and where you have application software. And these, of course, talk to each other, and these interfaces between clusters are handled via CPFlex. And yeah, so since there were requests from several OEMs, we decided, okay, we really need to standardize this to not have 5 different implementations for 5 different OEMs. And we started a concept in AUTOSAR, where Bosch and Continental proposed the AUTOSAR concept classic platform flexibility. And the first draft release of that was already in 2011. And since then it has been improved and validated so that it's no longer draft. So this is now part of the AUTOSAR standard. How does this independence look on the build side? So instead of a single ECU build where you get a single hex, you have a cluster build for every application software cluster. You have a host build, and you get pieces of the complete hex file. You merge them together, and in the end, you get again a hex and HL file. The build steps are independent and have no strict order. So you can build the host and then cluster 4 and then cluster 7 and then cluster 2 and then again the host. And it doesn't matter in which order you do these steps. And this also means that everyone who develops an application software cluster, for example, can, whenever he wants to regenerate the RTE, rebuild his cluster. And this offers a lot of benefits during development. And what are the parts? So I talked a lot about that this is a flexibilization in the RTE, but CPFlex is more than just an add-on to the RTE. So you have several important parts. You have the software cluster connection, or SW-CLUC, which is the interface between the RTEs, which offers the way to send messages from one cluster to the other, or to read data from another cluster, to call functions in another cluster. The other important ingredient is the system description, where you can define your clusters, which software components belong to which cluster, where are the interfaces, all of these things. And the third important ingredient is then the hex creation, where you take all your clusters, merge them together, connect the interfaces, and you can then flash them. So with this, let's switch over to Hosam for a quick demo on how this, how this works in practice.
Thank you, Jakob. So right now we will start with exploring what we have in our first version, which is 1.0, and explaining the different clusters for the host and the application, and which software component allocated to which cluster, and the basic software as well. And we'll try to use the virtual debugger, GDB, and explore first this is the execution of 1.0. Then we will add the newly mentioned runnable, and we will see the configuration process and the build process, and how the the application cluster will be linked to the host cluster. Then we will execute it again using the debugger. So first thing we will. Yes. So this one we will have here the two clusters, the application and the host. The host is mainly your normal one, contains normally everything you need with the basic software modules you need, some initial configurations, the common stack, and actual functioning working project. And within the application software cluster, we need as well some software components. For example, we have here the step control version 1.0, which only contains one main function. Need to mention that in the host, we need this secret and is a magical software component, which is the software cluster communication, which dispatches the call from the host to the application software cluster's software components. So let's see how with these configurations, what shall be the RTE from the application cluster. So we will see it like this. We have only two software component, two main functions being scheduled from the RTE. We have here the first one, the 1.0. Okay, so let's maybe start and see how it shall look. Just a little bit slow, but so based on this scheduling, we will start hitting the application software runnable, then we will hit the sleep control main function, which is allocated into two different software components. And within each one, just your simple logic and the logic you would like to do. Here we go. So based on the RTE, first we hit the application software, then we went to the sleep control. Okay, good. So let's right now we received the system description 1.1, and we are, as a development team, we were requested to add this new main function for detecting the leaf detector. So what we shall do, we will go to our software component. We will, in the main functions, we'll add a new runnable. It's here. So let the simple main function. And after that, we need to add some timing event. And this timing event will be linked directly to the leaf detector. Some periodicity. And within that, we need to add the access points as we will receive, and we will receive the flag for the leaf detector from the signal layer from the host itself. So we have some cross cluster ports. So we need to read these data through the ports, and then we will send back the torque through the signal layer as well. So we'll add we need some receive points and we need some send points. Just a normal access points using sender receiver ports. So what else do we need? We need to schedule this function. So after we already created this main function, so we will need to map it to the task. And these tasks from the application clusters. Okay, so what we will do right now, we need to generate the CPFlex, which will create the proxy calls, and then we need to generate the RTE as well. So from the application, we will and then build. Great. The second part shall be just generating the RTE. Good. Let's see how the RTE will look like right now. So yes, we shall see here that this task will contain the new added main function, and the CPFlex generators created the proxy codes which will be used the cross-core communication for scheduling the main function and calling the interfaces between the host and the application cluster. So the important right now is the build itself. So as Jakob monolithic build, but we will have a separate build for your application cluster and a separate build for the host. Normally the host, which contains everything you have, so it will take a lot of time. But from the application, it will only contain your software components, so it will be much faster. So the build is already built, and we will not build it again. But from the application part, we need just to rebuild it. We forget one thing, that we needed the implementation of the main function. I just adding everything here for simplicity. So we have here just the main function and the implementation. We will read some signal, and based on the logic, we'll just use and send the torque back. So just normal implementation, normal simple logic. So we'll just save this one. We will go to the application build. Let's clean. Good. Should be so fast. Good. So we have rebuilt the application, and the output will be just a library, and this library will be linked to the host. So right now, we just from the host we need to relink. So we'll delete the executables.
And the interesting thing is that you could get a binary of the host and of the other clusters. As if you develop just a small piece of application software, you could get the other parts as a binary and build your own cluster and then just link it together, and you have a running software. So you could even change the way that software is currently developed and have fully working hex and or binaries for everyone who works on a project. This is really a chance to also change the way we're currently developing software.
Exactly.
Just exactly. A lot of more flexibility.
Yeah. Thank you, Jakob. So we shall see here that we only need the linking step. Please. Exactly. So the new executable for the wall contains the host and the application clusters. So let's add a breakpoint here. Then let's see what shall be.
I mean, of course, this is a very, very small project, but even in more realistic projects, you basically have a turnaround time of maybe half an hour for a cluster. So it's feasible to work on a complete project. You only build what you need to build, and the linking step is also not that long. So maybe a minute or so. So you can have, if you start with a complete working solution and you're just incrementing on it and doing small updates or developing your own part of it, you have really very fast turnaround times here. And you only build what you need. You link it together, you flash it, and you have it running on a ECU, or in our case here on a virtual target.
Thank you, Jakob. So based on the scheduling from the RTE, we will first hit the application runnable, then the step control port 1.0, and then the leaf detector 1.1. So this is the first one, second one, and third one. So what is worth to be mentioned that if we're using splitting the RTE, it will just give you to work on your application. You will not worry how to be connected. This is an important thing. The second thing is just not using the monolithic build, and believe me, I'm suffering for building as a host again. I suffered a lot for building the host, so it will be one-time thing, and it just will be like linking. And as Jakob is saying, it's just 1 minute or so, and everything you will have the full. The full software contains everything. So I think this demo was helpful for explaining how powerful and flexible the CPFlex would be. Back to Jakob.
Yeah, so thank you, Hosam, for the demo. So yeah, what are the benefits of CPFlex, and especially of our ETAS way of doing CPFlex? You have shorter build times. You can resolve integration dependencies because the interfaces between clusters are a layer of abstraction where you can have version increases, and you can have interfaces that someone requests but the other cluster doesn't provide yet, and all of this is handled via CPFlex. You have a complete solution, so everything you need to do works in a single tool. You can change the system description in ISOLAR A. You can then add runnables as we saw in the demo, but you can of course also to add ports or even add complete software components to your local cluster. Everything within RTK 12.2. We have invested quite a bit of effort to get an easy start, a quick start. We will also be releasing a starter kit, so if you're interested in that, contact your local hub or contact us. There are tools in ISOLAR or in RTK that make it easy to start with a cluster and to define them and to define the interfaces and so on. But you have also seamless integration into customer workflows. So our tooling is very flexible and can be adapted to fit to how you do your system architecture in your projects. It's easy to use, and our implementation is standard conform. So you can look up the spec. I mean, we have Docker ourselves, but if you have any deeper questions, you can look it up in the spec, and it will work in the same way in our solution. And with that, thank you very much for attending and for the many questions. If you have any questions about CPFlex or just in general about how do I use AUTOSAR, you can get in touch with me. Here's my email. As I said, we are also releasing the CPFlex starter kit. So if you want to play with it yourself and get a feeling of, okay, what does it do? How does it work? You can get in contact with your local hub or Hosam and me directly. So yeah, thank you very much. Over to you, Hosam. You have final words.
No, thank you. Hopefully it will present it well, and it answers questions and give you a basic idea about the CPFlex and how powerful it is. And hopefully you would use it in your project, and we receive your feedback about it. Thank you.